Hello. Let's continue working on the subroutine we made last time. I'm even going to move the entire loop into this subroutine. We now have two labels that point to the same place, but they have a bit different purposes. And this subroutine is now something that takes two parameters. First one in EBX, the address of the sequence of characters, and the second one in ECX, the number of characters to shift. What this subroutine does is then simply add 2O to each one of these characters. And of course, when we make a subroutine for ourselves, we are free to pass the parameters in any way we wish. But if we want to call some procedures or functions from other libraries, perhaps operating system, or when we want to make our subroutine available to others, then we need to follow some conventions. There are several conventions depending on the context, and some of them indeed use registers for passing the parameters. But there is only so many registers, so when there are many arguments to a function, then we may need another method anyway. And the most usual method is to pass the parameters through the stack. So we can simply store these two parameters on the stack. We can even do this directly. There is a variant of push instruction that can push a number directly onto the stack. But now we also need to read these values here, because we need this address in EBX register. Well, this would be wrong, because the value here on the top of the stack is the value that was put by the call instruction there. This is the return address, which is going to be used by read instruction. So this parameter is in fact 4 bytes up the stack, because the return address is 32-bit. In fact, every value on the stack is going to be 32-bit. And we can use this kind of addressing. This number added to register is called displacement. So this is an indirect addressing with displacement. And so the second parameter, we need it in ECX register for the loop instruction. And we can read it in a similar way. It is going to be even further up the stack at the offset 8. And one more thing. After we return from the subroutine, these values are still going to be on the stack. We could then perhaps pop them somewhere, but we do not really need to get those values anywhere. So instead of doing pop instruction, we can just adjust the top of the stack by 8, because 8 is the number of bytes that these two parameters occupy on the stack. Each one of them is 32-bit value, that is 4 bytes. Let's try it. So now we store value 3 on the stack. Now we store the address on the stack. We enter the subroutine. You can see that the debugger is automatically showing that this is accessing the first argument on the stack. And yes, EBX is now the address of the sequence of characters. And now ECX is 3. So the loop does its job, and we return from the function. We still have the parameters on the stack, but with this instruction we restore the stack. This detail is also part of the convention. Some conventions require that this is the subroutine that restores the stack to where it was. And how the subroutine can do it? Well, the return instruction is allowed to take additional parameter, a number that is exactly the number of bytes that need to be restored, taken off the stack after returning. So this is equivalent to what was before. The difference is that this is now the subroutine that restores the stack and not the caller. Let's quickly come here to return and see. We have these two parameters on the stack and the return address, and this single return 8 instruction is now going to take all this off the stack. Okay. Now, there is one possible problem with this method of accessing the parameters from inside the subroutine, because when we now need to operate on the stack for some reason, let's say that we need to preserve a register. We are going to talk more about this later. Then we are changing the value of ESP, so we need to use different numbers here, and we would need to keep track of this whenever we do something on the stack, that these numbers may change. So accessing parameters this way is quite hard, and for this reason it is usually done a bit differently, with help of BP register. In the beginning of the subroutine, we simply copy ESP to EBP and use EBP to access the parameters. So now when we do something on the stack, like storing register, we can still use the same displacements with EBP safely. But there is still one more detail, because the caller might also be using EBP for a similar purpose. So it would be better if we preserved EBP too. Let's do without this for a moment, for clarity. When we preserve EBP this way, then we have additional value on the stack before we have copied value of ESP into EBP. So we need to take this into consideration and count the parameters from 8. So this becomes 4 becomes 8 and 8 becomes 12. Because at +4 we now have the stored EBP address, and at at EBP we now have stored previous EBP address, and at EBP +4 we have the return address from the subroutine. This is the sequence. Now, when we do it this way, and we are free to operate on the stack and modify ESP register without breaking this method of accessing the parameters, we can, for example, reserve additional space on the stack for other purposes. And now we have some additional values before EBP. So now EBP -4 is some local variable. And we can access these local variables this way, just like we access parameters on the stack. But of course, since we reserved this space on the stack, we need to restore it later at the end of the subroutine. We could do it this way, but we do not even have to remember that this was 8 bytes reserved on the stack, because we can simply restore ESP taking the value of EBP. Just to test it, let's store something in one of these local variables. We are now going to have an error here. We need to specify the size of this memory operand, because when we just give a number, then the assembler does not know what is the size of this memory. This is going to be double word, because x86 was originally a 16-bit architecture, so word was for 16 bits, so double word is for 32 bits. Or 4 bytes. And now let's test it. We enter the subroutine. We store EBP on the stack. Move ESP to EBP. Reserve some additional space on the stack. And now in this additional space we store this number just for testing. Yes, it is stored here. Now we access the parameters. the usual loop. And now we restore ESP from EBP, so this reserved space is going to be freed now. We restore previous value of EBP from the stack, and we return from the subroutine, freeing the space taken by the arguments. And this sequence is so standard that it has a specialized instruction in x86. This entire sequence can be replaced with enter instruction with parameter 8 and 0. So this first argument to enter is the size of the additional space reserved on the stack at negative offset from the EBP. And the second argument has to do with nesting, when we want to copy some parameters from the same kind of frame of the outer procedure that called this one. So we are not going to discuss this at the moment. And then these two instructions at the end can be replaced with leave instruction. Let's see if it really does work this way. So now we are inside the subroutine, about to execute enter instruction. We have on the stack return address and two parameters. We execute enter. Now we have previous value of EBP stored and reserved 8 bytes. We can store the value here, read the parameters, execute the loop, and now leave instruction is going to restore the stack and EBP register. And now return. Everything works. Now, this calling convention, where we store parameters on the stack and callee restores the stack, not the caller. This is stdcall, used by default by 32-bit subsystem of Windows. Another detail about stdcall convention is that it allows ECX and EDX registers may be destroyed. And also EAX, because this register is used to return value from the function, but here we do not return any value. And therefore we are using EBX here, so we would need to preserve this EBX register, just like we had before. To conform to this convention, we would need to preserve EBX, or simply not use it. We can, instead of EBX, use EDX here. So we are now not using EBX, and we do not need to preserve it. Now we have a working subroutine in stdcall convention. Now let's try calling some function of operating system that uses the same convention. Let's take a look at one of the examples that comes with FASM. The most basic one. You can see here that it calls some functions of the operating system, and this is indeed stdcall. We push values of some parameters and execute the functions, but we call them indirectly, and this is because in the PE format of executable we use this import section to let the loader know what functions it needs to find for us. Let's copy this into our program. You can learn more about the structure of import section from my advanced tutorial about PE format. I'm going to link it in the description of the video. For now, all that we really need to know here is that these values, this may be new command for you. Just like we have db for data bytes, here we have dd for data double word. So every single one of these values is a double word, not byte like here. And these values are going to be replaced by the loader with addresses of functions in these libraries. So when our program contains such import section, then operating system is going to load these libraries, find the function with these names, and put their addresses here. So then we can call indirectly by calling this address. This is the label of this value. This is another new thing. Usually we would write label with a colon character, but with commands like db or dd, it is possible to put the label just before it. And then this label has the size associated with it. So the assembler knows that this is a label of a double word. So we can call this function. We can look it up in the documentation of Windows API and see that it has a single parameter, exit code. So let's just put 0 here as a value of this argument. And the other function that we have imported is messagebox. This is one of the functions that comes in two variants, A for ASCII and W for wide encoding of text. We are going to use ASCII, but let's take A off this label, so we can just use this name. This is a function that takes 4 parameters. Handle to the window, we can put 0 here. We do not have a window. Address of text, address of title. Well, we have a text at the address example, so let's use this one. This text needs to be a sequence of characters that is 0 terminated, so let's put 0 at the end just to make sure that it is not a longer text. And the style of message box, we can put 0 here also for the time being. Let's do not crash the program and just try running it like that. It has created a message box with our ABC text, and this is ABC text after it has been converted with our subroutine to lowercase. So we now finally have a program that does not require a debugger. It does something we can see. We can also add here this modifier to get rid of the console. This marks our PE file as not a console program but a graphical program. And that perhaps is enough this time. Thank you for watching.